Hello friends, good morning to all of you. I am Kshitij Vatham and in today's lecture we are going to study circular motion. Okay, so this is part of chapter Laws of Motion, chapter number 5, Physics, CBSE and CRT for class 11th. So before I start, I would like to request one and all to subscribe to our YouTube channel and click on the bell icon to receive the future notifications. I also request you to share our YouTube channel so that maximum people can find use out of it. So we will start with centripetal force. Okay, so before we move to centripetal force, we need to talk about centripetal acceleration. Okay, so whenever a body is moving along a circular path with constant speed, so there will be an acceleration acting towards the center of the circle, and that acceleration will be called as centripetal acceleration. Okay, so there has to be two things: a body moving along a circle, number one, and number two, it should move with constant speed. Okay, and from the second law of motion, we can figure out if there is a centripetal acceleration, there should be a centripetal force as well. So centripetal force F will be given by mb square by r, mb square by r. So what is m? M is the mass of the object, v is the constant speed of the object, and r is the radius of the circular path. Okay, so this is centripetal force, and centripetal force is applicable at multitudinous places. Like whenever we talk about merry-go-round, so there will be a centripetal force. Okay, and whenever we are talking about rotation of the planet Earth around the sun, or any other planet around the sun, is an example of centripetal force in action. Stone rotated in a circle by a string will also be involving centripetal force, and car taking a circular turn on a horizontal road will also involve a centripetal force. Okay, so how the centripetal force be obtained in these three cases? Which three cases? Case number one, stone rotated in a circle by a string. From where we will get the centripetal force? We will get the centripetal force from the tension in the string. So what is tension? Tension is the restoring force in a string. Tension is a restoring force in a string. It will provide the necessary centripetal force in case a stone is rotated in a circle by a string. Okay, second example, motion of a planet around the sun. So whenever a planet is moving around the sun, so in that case, the gravitational force of attraction between the planet and the sun will provide the necessary centripetal force. Okay, and third example is car taking a circular turn on a horizontal road. Okay, so in this case, from where we will get the centripetal force? We will get the centripetal force from the frictional force, force of friction between the tires of the car and the road will aid in providing sufficient centripetal force for car taking the circular turn on a horizontal road. Okay, so we will move to next slide. Motion of a car on a level road. Okay, whenever a car is moving on a level road, there will be three forces in action. Which three forces? One force is the weight of the car acting downwards, that is mg. Other force is the normal reaction that will act upward perpendicular to the surface in contact, and there will be third force, friction force between the tires of the car and the road, and there will be three forces. Okay, so now we know that there is no vertical movement of the car. There is no vertical movement of the car. So what will happen in this case? Since there is no vertical movement, n will be equal to mg. Normal reaction will be equal to weight of the car. Okay, and now since the car is moving along a level road and taking a circular turn, okay, so in this case the static friction between the tires of the car and the road will provide the necessary necessary centripetal force. Okay, friction force should be greater than the required centripetal force. If friction force will not be greater than the required centripetal force, what will happen? The car will leave the circular path. Car will leave the circular path. So we know that friction, which friction will be in the place? Static friction will be there in the place. So we will get the second equation. Second equation is mv square by r is less than equal to mu suffix s into n. Okay, so we got two equations, n is equal to mg and second is mv square by r is less than equal to mu suffix s n. So from the first equation we will put in second equation. Okay, so we will get the b square. By solving we will get b square is equal to, b square is less than equal to mu s rg. Okay, and by solving we will get v is less than equal to under root of mu s rg. Or what is mu s? Mu s is the coefficient of static friction between the tires of the car and the road. R is the radius of the circular path in which the car is turning, and g is acceleration due to gravity. So this is the maximum safe speed of a car in a circular motion on a level road. So maximum speed has to be less than or equal to within square root mu s rg. Okay, and one thing that needed to be noticed is that there is no involvement of mass of the car. Okay, so maximum speed of a car is independent of the mass of the object. Okay, so in case speed of the vehicle taking a circular turn on a level road is greater than under root mu s rg, so what will happen? The vehicle will leave the circular path and it will skid. Okay, so now we are taking static friction into consideration. It is in fact the static friction between the tires of the car and the road that will provide the necessary centripetal force. Okay, it is the static friction. In case this static friction is not present, what will happen? The car will leave the circular path. Okay, so now we will talk about motion of a car on a banked road. So what is meant by banking? So whenever we are raising the outer edge of the road higher than the inner edge, this is called as banking. So this is called as banking. We are raising the outer edge higher than the inner edge at an angle theta. So this angle is called as the bank angle. Okay, so banking is a phenomena in which the edges are raised for the curved roads above the inner edges to provide the necessary centripetal force to the vehicle so that they can take a safe turn. Okay, so when we will use the banking, we will use the banking in case the frictional force between the car and the road is not enough to provide the necessary or sufficient centripetal force. So what we'll do in that case? We will provide the banking of the road. We are going to raise the outer surface higher in comparison with the inner surface. So what will happen? We will study it mathematically in our next slide. So what will happen? You are raising the outer surface higher in comparison with the inner surface at an angle theta. Theta is the angle of banking. Okay, so what will happen? So in this case, this is the free body diagram. This is the free body diagram. Okay, mass will act downwards. Mass is acting downwards. Normal reaction will act along this direction. Okay, friction will act parallel to the surface in contact between the car and the road. This is friction. Okay, so now normal reaction. So theta is the banking angle. So this angle will be theta and this angle will be theta. This can be simply understood by using geometry. So we will resolve F and N into two components, horizontal component and vertical component. So N will be resolved into N cos theta and N sin theta, and F will be resolved in F cos theta and F sin theta. Okay, so now we know that there is no vertical movement in the car. There is no vertical movement in the car. So when there will be no vertical movement in the car, we will get first equation as r cos theta minus ka r mu s sin theta is equal to mg. By taking r common, you will get r within bracket cos theta minus mu s sin theta is equal to mg. This is the first equation. And now this component will provide the centripetal force. So how will you get the centripetal force? You will get r sin theta plus fs cos theta is equal to mb square by r. Okay, so now this will provide the necessary centripetal force. So we will get equation number 2, r within bracket sin theta plus mu s cos theta is equal to mbm square by r. From the first equation, you calculate the value of r and put in the second equation. So you will get this equation. Okay, so now you will cancel m on the both side, and by rearranging you will get bm square is equal to rg within bracket sin theta plus mu s cos theta upon cos theta minus mu s sin theta. What is r? R is the radius of the circular path, mu s is the coefficient of static friction, and theta is the banking angle. Theta is the angle of banking, and g is the acceleration due to gravity. So you will get Vm is equal to within under root rg sin theta plus mu s cos theta upon cos theta minus mu s sin theta. What is to be noticed here? In the previous example, previous case, we got Bm is equal to rg tan theta. But in this equation, what we are getting? In this equation, the maximum possible speed will be higher than in the case of a leveled road. So that means what? That means on a banked road, car can travel with higher speed in comparison with on a level road. So banking help in improving the maximum speed at which a car can travel without skidding. Okay, so that means by banking up the road, you are able to travel at the higher speed than at the level road. I repeated this to emphasize the most important property that we can get from these two equations. Okay, so now whenever there is no friction, means we don't want friction to involve in providing sufficient centripetal force. So we will put the value of mu s is equal to 0 in this equation. So we will get BO is equal to under root GR tan theta. So what does it mean? So it means in case we don't involve friction force to provide the centripetal force, in that case, what is the maximum possible speed with which the car can travel? That speed is GR tan theta. That speed is under root GR tan theta. That means in case the maximum value of the speed becomes greater than under root GR tan theta, we need friction force to provide the necessary centripetal force. Okay, but in case the value of the speed of the car is less than or equal to GR tan theta, we don't require F to provide the centripetal force. F means friction force. We don't require F to provide the necessary centripetal force. That means when a car will move with the speed less than or equal to under root GR tan theta, in that case very little wear and tear of the tires will take place. I hope you understand this. So now bending of a cyclist. Okay, so whenever a cyclist is taking a safe turn, so it has to bend a little from its vertical position. So what I mean to say, in banking of the road, we are having a component of the normal reaction to provide the centripetal force. In the same case, in the bending of the cyclist, there will be a component of the normal reaction that will provide the necessary centripetal force. In the first case, we were banking the road, we were raising the outer surface of the road higher in comparison with the inner surface. And what will happen in the bending of the cyclist? The cyclist is going to bend at some angle theta with vertical, and in that case, the one component of the R will balance the mg, another component of the R will provide the necessary centripetal force. So this is the diagram. So this is R. So and this is angle is theta. So R can be resolved into two components, r cos theta and r sin theta. Since there is no vertical movement, so r cos theta will be equal to mg and r sin theta will provide the necessary centripetal force. R sin theta will be equal to mb square by r. By solving, we will get tan theta is equal to b square by rg, or theta is equal to tan inverse within bracket b square by rg. So this is the angle with which the cyclist should bend with respect to the vertical. Okay, this is bending of a cyclist. Hope you are able to get the concepts of circular motion with respect to force and laws of motion. See you soon in our next video. Thank you very much. Thank you.